So welcome to the seminar. This is the last one of the quarter. We are very happy to have Ruimeng Hu, whom everybody knows from our department in mathematics at the same time, joint appointment. And she will talk about convergence of empirical measures, mean field games, and signatures. So Ruimeng, not the floor, but the screen is yours.
Okay. Well, thank you, Jean-Pierre, for the nice introduction, and thanks for having me here to present my work. So this talk will have two parts. The first part concerns about a general metric measuring the convergence speed of empirical measures, and this is a joint work with Jie Quanhan and Ji Haolong from Princeton. The second part will talk about algorithm, a deep learning algorithm for mean field game with common noise, and this is a joint work with Ming from our own department. Okay, so let me start with the first one. So for the first part, again, I'm concerning about the convergence speed of some empirical measures to the true distribution. So mathematically, let's take a mu to be a probability measures on the RD space where P is with the P's finite moments, and mu n bar is the empirical measure of this n samples x1, x2, and xn drawn from this distribution mu. And we know that under many metric or distances, we have the empirical measure converge to the true distribution as we have sufficiently enough samples, as we have many samples. And we in this first part, we actually want to have some special properties for this phi, this metric, such that we want this convergence to be free of the dimensionality D. Okay, so why are we interested in this problem? So I think this plays an important role. I mean, this convergence of empirical measures. First of all, if you want to learn a distribution from finite samples, you want to recover the distributions after observing finite samples, then you want to know how fast you can recover the real distributions. And also it is used to measure the propagation of chaos of this n-particle system to the Makin-Vlasov type system. And also we will talk in more details later. If you are interested in study a homogeneous n-player game, and when the number of the players is large enough, then of course you want to turn to mean field games, use the solutions to this mean field games to construct some epsilon Nash equilibrium, to construct some approximated Nash equilibrium, and then how close this Nash equilibrium is close to the true one, then this all related to how the empirical measure converge to the true distribution. So to me, this is a very interesting topic, and let me explain why I'm now sticking to this Wasserstein metric. So, so the first is a definition, the quick review of this P Wasserstein metric, where this is the infimum of all the P's distance between x, y, where gamma is all the couplings between mu and mu prime. Some two probability measures on RD space. Okay, and we know that this Wasserstein metric is widely used in analyzing optimal transport related problems, and also in machine learning. For example, there's a nice work of Wasserstein again, and but it also has some potential problems in high dimensions known as this curse of dimensionality. So below I have two examples here talking about the convergence speed of these empirical measures. So we know that if we are using one Wasserstein distance to measure these two distributions, and if we assume mu has at least two finite moments, more than second moments, then this convergence will have an upper bound, which is of order 1 over n to the power 1 over the maximum between D and 2. I mean, the upper bound would be affected by the dimensionality, and the higher the dimension of the underlying space, the slower the speed, the convergence speed. And we have the same upper bound for the two Wasserstein distance. So then the question is, can we have a metric B phi such that this convergence is free of the dimensionality? Okay, and so this is the goal for the first part of the talk. Okay. So before talking about the our proposed metric, let's take a step back and then look at another object here, which is called the maximum mean discrepancy. So this definition has been frequently used in high-dimensional data processing. So given two sets of high-dimensional data, this is a widely used criterion to measure whether these two data sets are from the same distribution. So there, they measure the two distribution mu and mu prime in the following way. So they take f to be some testing function space, and then they measure the distance between this f integrating with respect to these two different measures. And in particular, they use the unit ball of this reproducing kernel Hilbert space for easy computation. Okay, so a quick recall of this reproducing kernel Hilbert space. The calligraphic age is a RKHS if for all the functions here and for all the x in the RD space, this linear point evaluation functional mapping exists and continues. Continues. Okay, and one can always use a kernel, positive kernel, to define the reproducing kernel Hilbert space by the following. Okay, and one famous example is always this Gaussian kernel, which is given here. Okay. So why am I mentioning this MMD? Why am I mentioning the maximum mean discrepancy here? So first of all, we notice that by the duality of this Wasserstein distance, we can also express the one Wasserstein distance by the following. It can also be expressed as the supremum over some test function class of this integral between two different measures, where here for the one Wasserstein distance, the phi would be all the continuous and functions with Lipschitz constant that is less than or equal to 1. So then we immediately have some common facts between common forms between this Wasserstein distance and one Wasserstein distance and this maximum mean discrepancy. So they both share the same structure, but they choose different test function class. Again, for the one Wasserstein distance, phi is the one Lipschitz functions, and for the maximum mean discrepancy, phi would be the unit ball of the RKHS. Okay. So the definition for the GMMD, the generalized maximum mean discrepancy, starts from this common structure here. So our idea is to prescribe some assumptions, criterions on this test function such that we can have the convergence of the empirical measure to be free of the dimensionality. Okay, and all the results in this part are from our paper on the archive. Here is the reference. Okay, so let me talk about the definition first. Again, we still take this as a structure which is common seen in the GMMD and one Wasserstein distance, but we will require the following 3 items for the test function class phi. So first of all, we want this class to be rich enough such that if I'm integrating a sign measure over this test for all the testing function which give me 0, then this has to tell me that I have a trivial measure here. Okay, and secondly, I need to ensure some integrabilities. So I want to have this phi function, this f function to be Lipschitz with the constant Lipschitz constant a1, so that the right hand side of the supremum will be finite. Okay, and most importantly, we describe the richness of this class by this empirical Radmacher complexity. Okay, so given a test function phi and n samples on the RD space, the the empirical Radmacher complexity is defined to be the average of this expected of the supremum, where this C follows the Radmacher distribution. It's simply it takes value 1 with probability 50%, and it takes -1 with another 50%. Okay. And we explicitly require this empirical Rademacher complexity to be bounded by a constant divided by n multiplied by this square root thing. So from here, we can immediately feel that the class here, the phi class here is smaller than the 1 Lipschitz class. And this is why later on, when we show the convergence, we would not feel the cursive functionality. We cannot see that the D appears in the convergence. So if we were taking this phi to be the 1 Lipschitz function, then on the right hand side, you will have this n to the some power, where the power will be dependent on the dimensionality. So here, by having this assumption, by having this criterion, we explicitly we already shrink our test function class to be smaller than the class that define this 1 Wasserstein distance. So then a very quick example of computing the empirical Rademacher complexity. So if you take the phi to be some function which is a linear product between x and some weights, where the 2 norm of the weights is less than 1, then just by Cauchy-Shirov inequalities, we can compute the empirical Rademacher complexity to be bounded by the maximum of the L2 norm of all the samples here divided by n. And since we start definition for this GMMD from the common structure of the MMD and Wasserstein distance, then we are able to show that under proper conditions, this MMD which use the measure the distance of the probability distribution using the RKHS space is an example of the GMMD if the kernels satisfy some nice properties. So basically, you want to have some K1 and K2 constants, which will be related to this A1, A2, A3, which are the criterion from the GMMD. Okay. So I won't talk too much on the details here. And later on, I will also show some other class of functions which can serve as the criterion, this test function class phi. And I will mention that all of them are closely related to the objects in the deep learning. Okay. So what can we do for this GMMD? What can we say about this new metric which measure the distance between two probability distribution? So first of all, by the definition of this GMMD, we immediately have this metric can be bounded by A1 multiplied by the 1 Wasserstein distance. This is simply because all the test function here, in phi are A1 Lipschitz. So we just use that property, and from the second one to the third one, this is by the relation between 1 Wasserstein distance and a 2 Wasserstein distance. Okay. So the more important results are the part B and part C. So for part B, we give explicitly the upper bound of this convergence speed, which on the right-hand side, you can see this rate of convergence is of the order 1/√n, where you do not see any D explicitly. And we can also have the convergence of the square of this distance from the mu bar n to mu. Okay. And moreover, if we have this mu to satisfy some transport inequalities, then we can also give some concentration inequality in this way. And examples of mu which satisfy this transport inequalities are like Gaussian distributions or sub-Gaussian distributions here. So some small discussions about how to obtain this. So as I mentioned, for the part A, that's straightforward by definition of this test function class phi and the relation to the one Wasserstein distance and two Wasserstein distance. For part B, in order to obtain the first inequality, this inequality, the first one, okay, we first bound this definition, the distance between mu and its empirical counterpart by this empirical Radmacher complexity. This is a very classical inequality, and then immediately we can use the criterion 3 in the definition of GMMD, and then we can get the first inequality. Okay, and for the second one, we instead compute the variance of this part, where the second moment then is simply the variance plus the square of the first moment. And then to compute the second moment, we use this famous Efron-Stein-Steele inequality, where here you have both the x1, x2 until xn, and this y1, y2 until yn. So those are another set of random variables that are drawn from the distribution mu, where they are also IID. And then for part 3, for this concentration inequality, we simply define this G function, where we know that the G function is Lipschitz, and it has Lipschitz constant to be A1 divided by N. And then we can use some already established inequality, some concentration inequalities. In particular, some results in the paper by Dula-Schulecker and Radmanen, where they talk about the concentration inequalities for mean field game and mean field particle system, and we can immediately get the same type of results here. Okay. So these are the sketched brief steps to obtain those results. Now let's see what are the other test function class that can be used to measure the distance between those probability measures. So the first one that are also satisfy the 3 criterion here is called the Barron space. So Barron space is closely related to this 2-layer neural networks. So we can view the Barron space as the limiting of the 2-layer neural networks, where the number of the neurons in the hidden layer tends to infinity. Okay, so you basically have these 2 representations, whether for any f in the Barron space, the f can be represented by this integral, where phi is some measure on this SD space, and for in our particular proof, we use sigma to be the ReLU, the ReLU function. Or you can also interpret this Barron space to be the closure of all the finite all the 2-layer neural network 2-layer neural networks with a finite neurons in the hidden layer. Okay. And to be more generalized, we can also take the generalized Barron space, which are defined on top of the Barron space. And this is the continuous version of the multi-layer fully connected neural networks. So if you are taken, think about a 3-layer neural network where the hidden layer, the neuron in the hidden layer tends to infinity, then this can be viewed as a function in the generalized Barron space. Also, we can also set the test function class to be the flow-induced function space. This is the limit case of the residual neural networks, where the depth of the neural network to be infinity. Therefore, you can think about this output of the residual neural network to be the solution of some ordinary differential equations. And that space is called flow-induced function space. Okay. So the other question we want to ask is, can we have something more if we already get some distributions that are close to the target distribution in the GMMD sense? So from the definition, we know that the GMMD metric is always bounded by the Wasserstein distance. But in this particular type of models, which we call the bias potential model, then we are able to show that, suppose that your target distribution is a bias potential model. And this is something that you want to approximate or you want to learn, and you have some samples. And now what you already have is what you already construct is you have some approximation that is close to your target distribution in the GMMD sense. Then from the GMMD sense, we can build a new approximation that is close to the target distribution in the Wasserstein distance. So we can make the results to be stronger here. And this is particularly true at the bias potential model. Okay, so let me briefly mention these results here. So what is the bias potential model? So we need to have a known, first of all, we need to know base distribution P, and we want to have first moment here. Then we define this bias potential model using this Radon-Nicolini derivative, where now we define this phi of P to be all the function V in this test function such that this integral to be finite, so that the Radon-Nicolini derivative can be well defined here. Okay. And then we have the following results. So suppose that here mu is our target distribution, and suppose that mu can be expressed using V star. That means mu is in this bias potential model, and nu is something that we already know how to construct, and nu and mu, they are close to each other in the GMMD sense. Then for any V in this test function phi, then we define the laws for this V function to be the following. And then if we are able to take the argmin or the infimum here, then we are able to construct another measure which we denoted by nu prime. And we are able to show that the nu prime is also close to mu, and this is in the Wasserstein distance. So this is in a stronger sense. Okay. So in particular, if we have this P to satisfy this transport inequality, then the Wasserstein distance between the Wasserstein distance between the target distribution and the new constructed distribution nu prime can be bounded by the square root of the GMMD distance between the target distribution and the already known distribution nu. Of course, in reality, we can take this nu just simply to be the empirical distribution of the finite samples. And then from the previous result, we already know that this will be small enough of order 1 over square root of n, which is free of the dimensionality. Okay, and then we can also have a similar bound for the 2 Wasserstein distance. And then if we put stronger assumptions out on this based on the base distribution, saying that it satisfies this logarithmic sublift inequality, then we can have a stronger bound for this 2 Wasserstein distance. So previously, the 2 Wasserstein distance is bounded by the fourth root of the GMMD, and recall that we from the beginning we would require this GMMD to be small enough. Therefore, this will be the square root of the GMMD distance would be a smaller number. Any question? Okay. So the next would be a application of this GMMD metric to show that if we are interested in using the mean field strategies to mean field solutions to approximate a n-player homogeneous stochastic differential game, then the epsilon Nash equilibrium where the epsilon is also free of dimensionality. So let me start with some formulation. So if we are interested in the symmetric n-player game where the xi is this, the private state for the player I, and you have the private control alpha I to enter this private state process xi. And here we do not have the common noise. This wi are those individual noise. And X bar is simply the empirical distribution of all the players in this game. And everyone is trying to minimize their running cost plus some terminal cost, or maximizing their running reward plus some terminal reward. Okay. And then if we have n to be large enough, usually this game will lose the will soon lose the tractability, and the numerical is also not easy to get accurate results before the introduction of deep learning, I would say. So then people turn to the mean field approximation. So, but formally, by let n goes to infinity, we can get a mean field game version of this game where all this now we do not have the superscript I, and we would replace this empirical distribution simply by some distribution, which I will explain in a second. And the mean field game is actually nothing more than a stochastic control problem plus some fixed point iteration. So for a mean field game here, basically to find the solution for this mean field game, it's like you are given a probability measure, a flow of probability measure mu t, and you try to solve this. Then you view the problem as a classical stochastic control problem, and then you solve the control problem. But then you want to close loop by figure out mu such that if mu is the flow of measure that you are given to this problem one, and if you solve the problem one based on this measure, then you obtain the optimal states, then you want the law of your optimal state to coincide with the given measure in this equation one. Okay, and this is the fixed point part of this scheme. And if people are able to find the solution to this problem one, and then they can start using the mean field control, which we did by alpha here, to construct some epsilon Nash equilibrium, where epsilon Nash equilibrium is something that is close to Nash equilibrium. That means it's a set of strategies where if you deviate, then you can only increase yourself no more by epsilon. So you are almost like a Nash equilibrium. Okay. And for this application, we follow the model setup in a paper by Kimona and Dularu in 2013. So basically, we have some Lipschitz conditions on all those B, sigma, F, and G, and some convexity assumptions. But instead of having all these distance measured by the two-Wasserstein distance, we in our assumptions we replace it by the GMMD. Okay, and then we are able to show that still by solving the mean field game and then use the mean field game solution to construct a n-player strategies, then this n-player strategy will give us a epsilon n Nash equilibrium, where now the epsilon n is only a function of, it is only order of 1 over root of n. And but previously, if all the distance that's measuring the distributions are used of the two-Wasserstein distance, then this epsilon n would explicitly depend on the dimensionality.
It's 4 o'clock.
So this is like one main application that we think about for this application, for this GMMD metric. And in our paper, we also talk about the convergence of the processes, the empirical distribution of the processes to the true distribution. But let me skip that part, and if we have time, then I can come back at the end of the talk. But basically, if we are talking about the convergence of the n-particle system to these Marquin-Volossov type stochastic differential equations, then we are talking about the convergence of these stochastic processes. Then we, in addition to the moments that we required to have the convergence to be free of dimensionality, we also require some modulus of continuity for those processes so that the proof can go through. But let me go to the second part. But before start the second part, I would like to pause a bit and then to see if there's any question. Or okay. So the second part is about a deep learning algorithm for a machine for mean field game with common noise. So in the previous example, you have seen that for a n-player game, if the number of the player is large enough, then one can use mean field solutions to approximate the strategy in the mean field game. So the second part focuses on how to solve this mean field game, and in particular, when we have common noise, then how to deal with this conditional law, basically. So what are the additional ingredients here for the mean field game with common noise? So we are still facing some stochastic control problem, but now in this XT, which is the dynamics for the representative agent in this mean field game, we have not only the individual noise, which is described by WT, but also some common noise, which is commonly seen by all the agents or all the players in the game, and this is described by BT. So we would have two parts, and then we are still for solving the mean field game with common noise. There are still like two steps. First, you are given a flow of measures and you solve this problem too, and then you try to get this fixed point argument. But the difference here is that the common noise is seen by all the players, all the agents in this game. So when you are averaging everyone in the game, you are not averaging only the individual noise are averaged out. The common noise will still persist in the system. Therefore, the consistent condition is understood in the following way. So you want this given stochastic measure flow, the stochastic flow of measure, which appears in equation 2, to be coincide with the conditional law of this optimal path given this common noise. Okay. And in my paper, in this paper that collaborating with me, we propose some numerical methodologies to solve this problem using a concept called signature that is from rough path theory that can efficiently represent this conditional, not conditional law. We actually try to represent the conditional expectation efficiently using signature. So before talking about the our algorithm, let me briefly mention theoretically how mean field game or mean field game with common noise can be solved. So there are basically three approaches or two main approaches. The first one is you can write master equations. So master equations is a Hamilton-Jacobian-Bellman equation, but it involves the time variables, spatial variables, and also probability measures. So if you want to design some numerical algorithm on top of the master equations, then basically you need to deal with taking derivative with respect to probability measures, and then to do some discretizations of the probability measures. So there's some thing not quite clear how to do, or can be easily done. Okay, or we can also write down the Fouk-Planck Hamilton-Jacobian-Bellman system. So without common noise, we know that the mean field game can be characterized by a coupled PDEs. The first one is the Hamilton-Jacobian-Bellman equation is with a terminal condition, and it describes this the minimization problem that we are facing, and this Four-Planck equation is a forward equation that describes the evolution of the optimal trajectory of the optimal state. And with the common noise, the both component become stochastic. This is due to the introduction of the common noise. So now you have the stochastic Four-Planck equation and stochastic Hamilton-Jacobian-Bellman equation. They are still forward-backward coupling, and they both become stochastic. And there are not many results on solving those each individual things using deep learning, and let alone the coupling system. And the third approach would be to use stochastic to use the stochastic maximum principle, and then to transfer the game into solving a forward-backward stochastic differential equation of the Moquin-Vlasov type. And for this kind of reformulation, we usually require the convexity of the Hamiltonian if we are having the minimization problem, or we require the concavity of the Hamiltonian if we are having the maximization problem. Okay, so in our approach, we simply take the direct parameterization, and then we use signature to represent the conditional mean field that interact in the whole system. So for direct parameterization, this follows the spirit of a paper by Han and in 2016, which they present in a NeurIPS workshop. So basically, direct parameterization means that we want to parameterize this alpha simply by a neural network, and then the infimum over the strategies is recasted into the infimum of the neural network parameters that are parameterizing this alpha. Then if you have the infimum over all those weight and bias, those neural network parameters, then this infimum is usually obtained or nearly found by those stochastic gradient descent algorithms. And then, of course, numerically, we need to discretize everything. So the forward process, the xt is discretized using the Euler scheme. The integral is approximated by the Riemann sum, and then plus some terminal reward or terminal cost. Okay. Okay. So then this is the first ingredient in our algorithm. The second part is we are using the fictitious play in order to find the equilibrium in this mean field game. So fictitious play is a learning scheme that was firstly introduced in economics, trying to find Nash equilibrium for normal form games. So normal form games are static one period game where you have this famous prisoner dilemma. That's the example for the normal form game. And later that was adapted to mean field games by Cataliage and his co-authors. So they show that in fact, if you are having a mean field games and you update your the Four-Planck equation, the solution of your Four-Planck equation, this law of your optimal trajectory using the fictitious play idea, then they can show this iteration will lead to the solution of the mean field equilibrium. So here we also use this idea of fictitious play, and we use it in the following sense. We suppose that we are given some stochastic flow of measures, then say mu n, then we plug in this mu n into the optimization problem. So everywhere here, it will be replaced by this mu n. Then we solve the control problem as a standard. We solve the whole thing as a standard control problem. Then this will lead us to be the new optimal trajectory at the n+1 iteration, and then we will try to obtain this law at this n+1 iteration, and then passing this law by the signatures. So I would say the novelty here is how to express the conditional law, or how to express the conditional expectation efficiently by the introduction of signature. Okay. So signature is, so now let me talk about the third ingredient here, which is the signature. So signature is a concept in the rough path theory. As of X is the represent the signature of the path of the stochastic process X, where the case component here is simply the case iterated integral given here. And in the truncated signature is if we are taking the first M components of this infinitely dimension sequence. And if we are just taking the first M components, then it has dimensionality to be of this. So xk will have the dimensionality d to the power k, okay, where d is the dimensionality of X itself. And signature has many good properties. In particular, it can characterize this path uniquely up to the tree-like equivalence. And if it is unique if at least one dimension of the path is strictly increasing. So in reality, if we want to have this one-to-one correspondence, we usually work with the X, but plus one dimension, which is the time. Okay, so later on, we will just use notation xt hat, which is the combination of the time dimension plus the stochastic process itself. Okay, so by working with the X hat, we are able to say that the S of the signature of X hat is uniquely describe the process itself. And the whole idea here to use a signature to pass to efficiently describe the conditional law is the following. So we know that the optimal the law of the optimal trajectory given the common noise, which we denoted by mu t of n, this can be this is equivalent to say if we are given the signature of those Brownian paths, and this is approximated by if we are conditioning on only given the truncated signature of those Brownian motions. Okay. And for the last part, we will be approximating using some linear regressions. Okay. So this is the flow map. Let me talk a little bit more details before coming back to here. Okay, so actually in this paper, we are only able to have nice results where the interaction is through the conditional moments. So we only talk about where this mu, this interaction is given by some conditional expectation of this iota of xt given the common noise. Okay, and the general conditional law case is left for the future work. Okay. In this particular case, then we are able to show that for any small number epsilon, there exists a truncation or the depth of signature M and the linear functional L such that this conditional expectation can be approximated well by the linear functional acted on this truncated signature. Okay, and then in practice, this linear functional is approximated by the linear regression of the realizations of this iota of the function on the truncated signature path. Okay, so some advantage of having this linear functional at the nth iteration. So first of all, this is very efficient in the prediction for unseen common path. So for any omega tilde, which is not used in the linear regression or in the training of this deep learning, then we can quickly evaluate it using this those linear coefficients acting on this truncated signature, and then to get the new conditional expected value evaluated at the unseen common noise. And moreover, in the when we are using the fictitious play in the original definition, it is to average all the empirical, all the past empirical distribution, and then to use that as the given distribution in the stochastic control problem that you are solving in the next iteration, and to average this empirical distribution, or to average the all the conditional moments from the past, from the history. This is simply to average all the linear coefficients L from all the past. So this is the complexity is just simply order of 1. Okay. So now let me go back to this flowchart to further explain what the main steps here. So basically, for a given flow of measures, if we generate both the individual noise and then the common noise, and then we are able to solve this optimization problem 2, where the optimization problem 2 is simply this mean field gain with common noise that we are targeting, but then replacing the mu by this given conditional expected conditional expected expectation. And then for this given stochastic flow of measures, we are able to solve optimally this problem 2, and we can compute this optimal trajectory x, which we denote by xn. And then simultaneously from the initial simulation data, we can compute the truncated signature of those common noises. And then we approximate this conditional expectation by doing the linear regression of the iota of xn on the truncated signature. And from there, we are able to obtain this coefficients, which we denoted by ln. And then after this, we use the ln to update the ln bar, which is the average of all the linear coefficients from the past. And then we are using this ln bar to produce a new given flow, the stochastic given flow of measure mu hat, which will be the fit-in of the next iteration of the fictitious play. Okay, and from here we can usually generate more unseen common noises at the last step. So numerically, we test 3 examples that we try our best to test 3 examples which has closed form solutions and which are all a mean field gain with common noise. And in particular, this is an example by Daniel Lacker and his student. They examined the mean field gain of optimal consumption and investment, where it is a maximization problem of the Morton type. You are maximizing the utility of the consumption, which is denoted by CT, the consumption rate, plus the utility of the terminal wealth, where the pi is the strategy that you are going to the proportion of the wealth that you want to invest in the in this risky asset, and then CT is the consumption rate, the proportion of the wealth that you want to consume at each infinitesimal time t. And here they are using both power utility for measuring these 2 parts, and for the interaction with the population, the correct form would be to take the log of the rate and then to do the conditional expectation and then raise it to the exponential. So it's now simply to take the conditional expectation, but to take log first and then to raise it exponential later. Now, this is the right way to scale the problem to make it to be the explicitly solvable. And for this problem, we test our algorithms, and so these are the some numerical plots for each panels except the left bottom one. There are three trajectories. They use different random. They use different pair of individual noise plus common noise, and the solid lines are the true solutions from the analytical formula, and then the dashed lines are the approximation produced by our machine learning algorithm. And then you can see almost every, for every trajectory, the dashed line on top of the solid lines. Okay. And I want to explain the last one. You can see that the three lines are close to each other. Sorry. So you can see that for the last picture, the three trajectory are on top of each other. This is because for this conditional expected value, the consumption does not really depends on the common noise. So this is and this not depends on so that's why you cannot differentiate those from each other. And for the last panel, for this left bottom panel, this is the plot of the validation utility versus the true utility. So for validation data, we generate another set of samples, and we evaluate the realized expected value after from iteration to iteration of this fictitious play, and to compare it to the true utility, which is given by the analytical formula. And you can see that they are very close to each other in the end. Okay, so this is pretty much I want to talk about. Thanks for your attention. A quick summary and some future works, which particularly I feel interesting is whether we can derive similar results to the bias potential model, but for the GANs. But at the moment, this is still not clear. I mean, I'm not clear how to deal with it. Yeah, thank you.